Hello everyone, welcome back to the afternoon session. So this is the last tutorial talk of the bootcamp week. So in this class, we're lucky to have Professor Peter Glynn from Stanford University, the Department of Management Science and Engineering. So we know like in RL, so we always try to estimate some sort of conditional expectations or estimate the policy gradient. So we need estimation and simulation like basically in every single aspect of RL. And Professor Peter Glynn is going to teach us the basics of simulation. And we'll learn like how to potentially leverage techniques from simulation and Monte Carlo methods to be useful in reinforcement learning. Peter, it's all yours.
Thank you, Mingdi. I'd like to thank the organizers for this opportunity to speak as part of the RL Bootcamp. So I want to start by saying that my intention here is to give a broad overview in these talks of some of the tools that are available from within the simulation literature. So as such, I'm not going to be focusing on RL applications per se. The intention really is going to be to give a quick guided tour of some relevant research areas and to let you think about the potential implications for the RL community. So the outline for the first talk is going to be that I'll talk about the basics of simulation, aka also known as the Monte Carlo method. I'll talk about output analysis. That really relates to the question of how many samples do you need to take in order to have a reliable estimate of the expectation or probability to be computed. And then in the second talk this afternoon, I'm going to talk about what is known within the simulation literature as variance reduction. And I'll also talk about gradient estimation and a bit about stochastic optimization. So that's the basic outline of the two talks. So let me start with some basic terminology. So where does the word simulation come from? It comes from exactly the mathematical sciences view of the word simulation. Simulation is typically used to talk about a generation of trajectories of dynamical systems. Very simple class of dynamical systems are the deterministic dynamical systems that go with so-called autonomous dynamical systems. In the discrete time context, we would have the state of the system at time n+1 is some function of the state at time n. G could be linear or nonlinear. And of course, the continuous time version of that would be the differential equation d by dt of x of t, the derivative of x of t equal to some function of x of t. So in the world of stochastics, when we think about simulations, many of the simulations that one does are simulations of corresponding stochastic dynamical systems, in which now the deterministic recursion that I described up at the top of this slide is replaced by a stochastic recursion in which xn+1, the state of time n+1, is some function of the state of time n and some new independent noise that I'll describe as cn+1. So of course, we all know that this sort of stochastic dynamical system corresponds to a Markov chain. And if the CNs are IID, then I get a Markov chain with stationary transition probabilities. That's basically the plain vanilla type of Markov chain that we're most familiar with. And then of course, a continuous time variant of this would be a dynamical system in which dx by dt is equal to mu of x of t, and then it's perturbed by some white noise or random noise process c of t. And this, roughly speaking, is corresponding to the world of Markov diffusions or solutions of stochastic differential equations. So that is basically a continuous time version of a Markov chain. So in any case, simulation is all about simulating trajectories of dynamical systems, whether it be deterministic or stochastic. Now, one of the key important points to recognize in looking at simulation, in particular stochastic simulation, is its connection to the world of numerical integration. So in particular, if we're interested in computing some expected value of a performance measure W, some random variable W, where W, let's say, is some function of the trajectory of a Markov chain, xi, I ranging from 0 up to some random time horizon, capital T. Of course, the whole principle of stochastic simulation is to estimate that expected value by running independent computer experiments. In the world of simulation, these would be called replications. We run n IID replications, W1, W2 of W up to Wn, let's say, of the random variable W. So do n independent computer experiments and then estimate the quantity of interest, the expected value, as the average of the WIs obtained from these different independent simulations. So this is the basis of the so-called Monte Carlo method. I'll come back to that a bit later. Now, as I was suggesting a moment ago, if the xi's come from a Markov chain, then of course we can write down the state of the system in terms of the noise sequence C1 through C D if we have a time horizon D. And that means that the expected value of the random variable W that we're interested in, we're assuming now that that is some function of the state trajectory up to the time horizon D. And that in turn can be re-represented in terms of the noise sequence C1 through CD. And of course, that can be represented as a multiple integral, given that the CIs are independent of one another. So the HI of ZIs here are the, let's say, the probability density functions of the CIs, and we're integrating the function F tilde relative to those, that joint density. So a key point in thinking about simulation and thinking about Monte Carlo in general is that expectations can always, if we wish, be viewed as integrals, potentially over some high dimensional space. You can see in this context that the dimension of the integration that we're doing corresponds to the length of the time horizon. And of course, it could easily be that the simulation involves a Markov chain in which the CIs are most naturally vector valued. So if the CIs take values in RK, then effectively these HI of ZIs correspond to probability density functions on K space, and then we're doing a K times D dimensional integral. So in the world of simulation, it would typically be the case, almost invariably be the case, that this integration that we're effectively trying to do is very high dimensional. So conversely, if we have an integral that can be expressed as a integration over d-dimensional space, I can, if I wish, just multiply and divide through by the product of a bunch of probability density functions, in which case I can recognize that by multiplying and dividing through by this product, I can now recognize that this quantity here is being integrated against a joint probability density function on RD. And as a consequence, I can write this quantity alpha as an expected value involving the integrand that we are left with, in particular involving the expected value of Q of Z1 through ZD divided by the product of the HI of ZIs, where the ZIs have corresponding probability density function H sub I. So an important fact to recognize is not only can every expected value effectively be written as a high dimensional integral, but every integral can also effectively be written as an expectation. So there's essentially a one-to-one correspondence between computing expected values and computing high dimensional integrals. So simulation is all about using sampling-based methods to compute expected values. Expected values are in turn high dimensional integrals if we choose to view them this way, and as a consequence, simulation is really a class of methods based on sampling that is intended to compute high dimensional integrals. This is a method that got its name back in the Second World War from Stanislaw Ulam, and Ulam named this method after the Monte Carlo method. He was a physicist that was involved with the Manhattan Project, and Monte Carlo, of course, is evocative of the world of gambling and casinos and so forth. Monte Carlo being a very famous casino that existed at that time and still exists to this day along the Mediterranean. So from the standpoint of reading the scientific literature on simulation, it's important to recognize that when we talk about stochastic simulation, we're effectively talking about the Monte Carlo method. So when you look into the literature for references to this general area, you may oftentimes want to search under the terminology Monte Carlo. So we've already alluded to the Monte Carlo method. Again, the basic problem of interest is that we want to compute some expected value of a random variable W. And the basic idea is to generate IID replications to run independent computer simulations, W1, W2, Wn through W of the random variable W, and then to form an estimator corresponding to the sample mean. So alpha n here is just the average of the Wi's. And of course, one question that we would ask scientifically, mathematically, is why is this a reasonable method? Of course, reasonable should mean that the method converges as the number of computer experiments and number of replications n go to infinity. And of course, that's guaranteed by the law of large numbers. If the Wi's are IID, as we're assuming here, then the strong law of large numbers guarantees that if W is integrable, alpha n converges as the sample size n goes to infinity to the quantity that we're trying to compute. The more interesting question is how fast does it converge? And that's a question that's answered from the central limit theorem. So central limit theorem, of course, asserts that if we have random variables with finite variance, then and we scale the difference between the estimator of interest and the quantity we're trying to compute by square root of n, then that scale difference converges to a normal random variable with mean 0 and variance sigma squared. So that's a statement of the standard plain vanilla central limit theorem. And of course, if I unpack this weak convergence statement, so this is a statement in which the double arrow corresponds to weak convergence, or what's also equivalently known as convergence and distribution. If we unpack this, then we see that our estimator of interest, alpha n, is exactly the quantity we're trying to compute, alpha plus an error term. And the error term looks approximately like a normal random variable with mean 0 and standard deviation sigma over root n. And that has some profound implications. The fact that the error takes this particular form. Implication number one is that the convergence rate is slow. So in particular, if I want to compute alpha to, let's say, an additional significant figure of accuracy from what I might have currently with a given sample size n, we can ask the question, how much larger do we need to make the sample size to add an additional significant figure of accuracy? And of course, that means multiplying the current accuracy by a factor of 10. In other words, reducing the error by a factor of 10. And we see because of square root in the denominator, that as a consequence, we need to make n larger by a factor of 100. So every additional significant figure involves multiplying the sample size by a factor of 100. So Monte Carlo, i.e. simulation, is not a scientific computing method that is interesting to use in problems where you want high accuracy answers. But it may be perfectly suitable in settings where you're quite satisfied with, let's say, 3 significant figures of accuracy. Unfortunately, in the great majority of applications that many of us are interested in. We already have significant model error in the specification of the underlying stochastic model. The underlying stochastic model doesn't perfectly represent the real world. And so the idea of looking for 10 significant figure accuracy in a context where the model error is already significant doesn't really make much sense. 2 or 3 significant figures is often just fine. And so living with that relative inaccuracy of the Monte Carlo method is quite reasonable under the circumstances. Another thing that we can see is that the sort of underlying dimensionality of the random variables that we're sampling, the z's or the w's that we're sampling, doesn't come into this convergence rate analysis. So independent of the dimension, the ambient dimension in which the zi's or wi's are sitting, the convergence rate is always 1 over square root. That's something I'll come back to in a bit. Another very nice characteristic of this central limit theorem result is that the magnitude of the error of alpha n as an estimator of alpha depends on the underlying problem instance, the underlying distribution of the zi's or wi's, only through a single constant, namely the standard deviation of the random variable. So this is a particularly nice scientific computing context in the sense that the problem hardness is effectively characterized by a single constant, namely the standard deviation. So if you can make the standard deviation smaller, you get a more efficient algorithm. If the standard deviation is big, the problem is the expected value is going to be hard to compute. And then finally, the fact that the convergence rate is as slow as it is means that error assessment is going to be important. We can't just take the view that if we make the sample size n large, that we can reasonably expect that alpha n is necessarily going to be close to alpha. So as a consequence, we're going to want to do error assessment of some kind. We're going to want to be able to ask the question, can we scientifically take the view that the sample size n that we've utilized is large enough to have computed alpha to a reasonable level of accuracy? So that error assessment in the world of simulation, the world of Monte Carlo, is typically going to be enabled through a confidence interval. So most of this first lecture is going to be about different ways of constructing confidence intervals. So in particular, the central limit theorem that I just described, if you rewrite that central limit theorem, it basically can be rewritten to assert that this random interval centered at the estimator alpha n, so in other words, alpha n plus or minus something, is going to be asymptotically, as the sample size n goes to infinity, a 100 times 1 minus delta percent confidence interval. So if we're searching for a 90% confidence interval, delta would be 0.1. We would select z values from the normal distribution, so the probability that normal 0, 1 is trapped between minus z and plus z is 90%. And then having calibrated the z value in that way, this random interval will cover the true expected value roughly 90% of the time if n is large. Of course, the procedure that I just described is not practically implementable because in general, we don't know the standard deviation sigma. This whole simulation is being undertaken in order to compute the expected value of the random variable, let's say w. If we don't know the expected value of w, we're certainly not going to know the standard deviation of w. So the confidence interval that I just described is not an implementable confidence interval. But again, one of the beautiful things about Monte Carlo and beautiful things about simulation is that while we don't know sigma, it can be easily estimated from the sample itself. So internally from the sample, we can just estimate sigma squared, estimate the variance through the so-called sample variance. And There's the sample variance down here. This is how it's defined in the IID setting. And it's not hard to show that if you plug in a sample estimate for sigma, then when the sample size n is large, given that the sample variance converges almost surely to sigma squared as n goes to infinity, one can conclude that the confidence interval procedure that one obtains by substituting the sample standard deviation for the true standard deviation, again, has the property that it's an approximate, let's say 90% confidence interval when delta is equal to 0.1. So let me say a little bit more about this confidence statement. So this confidence statement relies on the central limit theorem, and the nature of this confidence statement is that it's asymptotic in the sample size n. There's a guarantee for any finite variance distribution that if we look at the probability that the expected value of interest is trapped inside this random interval that can be computed from the samples obtained through running n independent computer experiments, that random interval that takes the form alpha n plus or minus something, where the something is given by a z value from the normal table times Sn over root n. When we construct a confidence interval in this way, we have a guarantee from the laws of probability that the probability that that random interval covers the true parameter alpha converges to the specified probability as the sample size n goes to infinity. And of course, one of the things that we see in this statement is that there's no guarantee for any fixed sample size n. Now, in some areas of computational science and many areas of computer science in particular, people like having hard guarantees for fixed sample size n. And of course, that's something that is quite easy to do in some settings. So in particular, one way of potentially getting a hard error bound that you can use for fixed sample sizes n is to apply Chebyshev's inequality. Chebyshev's inequality in this context translates into the statement that the probability that the true parameter alpha lies in the interval alpha n minus epsilon over root n to alpha n plus epsilon over root n, but that has to be greater than or equal to 1 minus c squared over epsilon squared, provided that c squared is a bound on the variance of w. And of course, that's guaranteed if we know that w is a bounded random variable. So in particular, if we take c as the bound on the random variable w, then we have a hard error bound. So this is a quite satisfying result in the sense that we have a finite sample size n guarantee. However, there are a couple of problems with this bound from a practical standpoint. Number one is that many of the random variables, probably most of the random variables that one encounters in practice are not bounded random variables. And to actually a priori bound the variance of the random variable in a given simulation environment or a given computational environment might be quite challenging. It might be that it almost exceeds one's mathematical abilities to pull that off. But even if one can pull that off, it's pretty likely that the variance bound that you'll get will be extremely weak bound. And then if you were to plug that into Chebyshev, you'd get probably something that would be effectively unusable from a practical standpoint. So the basic challenge with using Chebyshev style arguments are almost, in fact, pretty much all of the hard error bounds that one sees in the world of sampling-based algorithms are based on assumptions that the random variables that are being sampled have known bounds on their support. And The one class of random variable that has exactly that characteristic and that actually do come up widely in practice, of course, are Bernoulli random variables, 0, 1 valued random variables. But outside of that class of simple such quantities, the types of bounds that one would get tend to be very, very loose, and that sort of leads one, from a practical standpoint, in the direction of using asymptotic validity to theoretically justify the algorithms that one uses. Now, it's probably also the case to some degree that part of why asymptotic validity plays such a big role in the simulation theory literature and in the Monte Carlo theory literature is that many of the people that have worked in the area were brought up, so to speak, within the statistics and probability worlds. And in that context, in those communities, asymptotically valid results are the standard bread and butter of those communities. So in particular, proving limit theorems involving weak convergence or various other types of results is the standard theoretical mode of analysis. And so to some extent, it's a cultural issue that relates to the focus on asymptotic validity rather than hard error bounds. But I think there also is a practical issue that hard error bounds in general would probably be close to unusable in many practical instances, even if you could compute a hard error estimate. Okay, so let me just say a little bit more about this dimensional insensitivity that I discussed earlier. So we talked about the fact that when you are computing expected value, that it typically can be represented as a high dimensional integration problem. And it's worth recognizing that, of course, high dimensional integration problems, there are all kinds, there's a very large literature on quadrature rules and various other things involving deterministic integration rules. So these deterministic integration rules typically involve a specification of various points in, let's say, the d-dimensional hypercube, where you would evaluate the function of interest, and then you might weight the function evaluations at these different points in some way. That would correspond to a weighted integration rule. And it's well known that if you look at the worst case error across reasonably behaved functions, so reasonably behaved functions in this case would be functions that are r times continuously differentiable with bounds on the various derivatives, that the rate of convergence in the computational budget C tends to degrade significantly as a function of the dimension D in which the random variables are sitting. So in particular, we see that the exponent up here has a 1 over D in it. That, of course, is the cursive dimensionality that we often hear about in various areas of computational mathematics. We do see that we get some gain from smoothness. The more derivatives we have, we get faster convergence. But the most important point in this result is the fact that you get extremely serious degradation in the rate of convergence when D gets large. All right, so that's what happens if you apply deterministic integration rules, things based on quadrature type ideas. What about if you apply Monte Carlo? Well, again, as I was hinting at a moment ago, we can apply Chebyshev in this context, and Chebyshev says that we can bound the probability that the Monte Carlo estimate deviates from the true quantity of interest by some quantity of scaled according to square root, as let's say epsilon over root n. That can be bounded by k squared over f squared, with k as a bound on the magnitude of f tilde. And of course, given a computational budget C, the number of uniform random variables that you can generate in a computational budget C is going to be scaling in proportion to C. But the number of d-tuples, the number of uniform d-tuples that you can compute obviously scales downwards by a factor of 1 over d. So the sample size, the total number of D tuples that we can generate in computational budget C. D grades as C over D, and as a function of the dimension D. And so there is some dimensional dependence in this result, but it's a very modest dimensional dependence involving this square root. So it's fair to say, I think, based on this analysis, that Monte Carlo tends to be quite insensitive to dimension, much less sensitive than this result is suggesting, where you have a 1 over D in the exponent. Now, I'd be remiss if I didn't mention to you that there's another alternative integration technology that one can apply called quasi-random sequences. Quasi-random, the use of the term random is a bit of a misnomer in the sense that these sequences are actually deterministic sequences that are intended to be deterministic. The fundamental structure of these sequences is such that they are chosen to satisfy a so-called equidistribution property. That means that if you look at the fraction of these ui's, so ui here now being a point in D space, the fraction of the ui's, let's imagine that D is equal to 2. So here's a unit square in dimension 2, and here's, let's say, an A point that corresponds to an A1, A2. And then we'd want the fraction of points, the fraction of ui's that fall into this little subrectangle to converge as the sample size n is the number of the chosen points n goes to infinity to the area of the subrectangle, which of course is just A1 times A2. So in the d-dimensional case, when D is greater than or equal to 2, we want the fraction of ui's falling to that hyperrectangle to be given by the volume of that hyperrectangle, which is just the product of the AI's. So it turns out that there are these equidistributed sequences that have the property that if I soup over all such A's, the maximal deviation between this the fraction of points in such an A hyperrectangle versus the volume is going to 0 at rate log n to the dth power divided by n. And that turns out that for a certain class of integrands that are have finite Hardy-Krauss variation, that the corresponding integration error also goes to 0 at rate log n to the dth power divided by n. And of course, this is a faster convergence rate in general than 1 over square root of n. So now I should mention that we have a log n here, and you could take the view that, as I think we often do, that log n is almost of order 1, and just disregard the presence of that log n. But you can see that when D is large, let's imagine D is of the order of 100, and you have log n raised to the 100th power, that number actually can be quite large. And as a consequence, when D is very big, you do get some, it is the case that this error bound suggests that this class of algorithms degrades to some degree. And as a consequence, when D is very, very big, I think it's still the case today that people view Monte Carlo-based algorithms in which we use purely random numbers to do our integration as being a better class of integration methods than what one gets through quasi-random sequences. The quasi-random sequences do have a good record for for successfully integrating integrands that have this finite Hardy-Krauss variation. It's basically a generalization of bounded variation in one dimension to the d-dimensional case. And in dimensions, let's say, up to order 50, some people would claim even higher than that, these types of methods can work very well and can successfully integrate with lower error than Monte Carlo in many contexts. So good to be aware of this basic approach. Okay, so now let's switch to the topic that will consume the rest of this lecture, which is output analysis, namely given that we have a simulation-based algorithm for computing some parameter alpha, how long do we need to run the simulation for to get a required accuracy? That's the whole question underlying the area of output analysis. So one thing to recognize again from a terminology standpoint is if you want to compute an expected value, and let's suppose that we're in a setting where the random variable W is simulatable, so we can simulate IID copies, W1, W2 to Wn, and then just estimate the alpha expected value through the sample mean. In this setting, there are really two types of procedures. So-called fixed sample size procedures, where we choose a priori the sample size n, and then at the end we construct a confidence interval that in general is of unknown size a priori. So after you've run the fixed sample size procedure, it could be that you got a big confidence interval, it could be that you got a small confidence interval, you're not quite sure before you run the procedure as to what the size of that confidence interval will be. That's a fixed sample size procedure. Now, from a scientific computing standpoint, it's often the case that we prefer to set the precision or tolerance first. That corresponds to the world of so-called sequential procedures. So in a sequential procedure, we first choose the error tolerance epsilon. And what does epsilon basically correspond to here? It corresponds to the width of the confidence interval. So we decide a priori, I want the confidence interval to be, let's say, plus or minus 0.1. And now we're going to generate samples until the confidence interval has that required size. And it turns out that at least as epsilon goes to 0, that there are many different types of results that suggest that these types of procedures are asymptotically valid as epsilon goes to 0. And the first of these results was due to Chow and Robbins in 1965, and there's been quite a bit of follow-on work since that time. So in the remainder of this lecture, I'm going to focus exclusively on fixed sample size procedures, but for virtually everything that I will talk about, there would be a sequential analog to this output analysis method. So the very first setting that we described was the setting of IID replications. Now we're going to talk about smooth functions of expectations. That's the second setting in which a more complicated setting in which one often wants to do output analysis. So in this context, the parameter of interest is some smooth function of a vector of expectations. So imagine Z as being RD value. The natural estimator, of course, is just to use a plug-in estimator, just estimate expected value of Z through the sample average of the random vectors Z bar n, and then to plug Z bar n into the G function, and that then will be our estimator alpha n. And now to analyze the large sample behavior of alpha n, we recognize that Z bar n is going to be close to the expected value of Z, and if G is smooth, we can do a Taylor expansion of G of Z bar n around G of expected value of Z. And then of course we get this as the first order term in the Taylor expansion. Of course, the central limit theorem says that Z bar n minus expected value should be of order 1 over root n. And it turns out that the second order terms in this Taylor expansion will involve terms roughly of the square of this deviation. That's just a consequence of Taylor expanding. And of course, that means that since Z bar n minus expected value is of order 1 over root n, all of those additional terms will be small relative to 1 over root n. In other words, little o of 1 over square root of the sample size. So that suggests that alpha n minus alpha basically is largely explained by this piece. And of course, this piece is just a deterministic gradient multiplied by a mean zero random variable. And now the central limit theorem applies exactly to the analysis of such quantities. And as a consequence, we can observe that we have a central limit theorem then for alpha n, in particular, square root of n times alpha n minus alpha divided by an appropriate estimate of the standard deviation sigma arising in the central limit theorem. That normalized so-called pivotal quantity converges to a normal 0 when n variable as the sample size n goes to infinity. And we're of course making the assumption here that we have a good way of constructing an estimate of the asymptotic variance of this estimator. Now, we will note that the asymptotic variance that we're trying to compute, the sigma squared, involves the variance of the gradient of g evaluated the expected value of z with z minus expected value of z. This thing, so this variance is going to involve the covariances, the covariance structure of this random vector, and it's going to involve the gradient. So these are both somewhat complex quantities to estimate or to compute in at least some applications, and as a consequence, this is the first of the settings that we will see in which you might want to avoid having to construct an estimator to explicitly estimate this variance, and we will come back to simulation-based methods that allow one to avoid having to try to estimate this very messy variance quantity that arises in the smooth function context. So here's an application. We want to compute the expected infinite horizon discounted reward corresponding to a Markov chain X. R is the reward function. E to the minus alpha I is the discount factor. And of course, this Markov chain, if we start off at some state X, eventually we'll come back to this state X. It'll take tau of X steps for that to occur. And once we get back to this point, things effectively regenerate. And as a consequence, this quantity alpha can be written in the following way. We have the expected reward up to the time that we come back to the state X, plus everything that is earned from the hitting time of X and onwards is discounted down by this common factor. And once we're back at the state X itself, the system regenerates. So the expected reward from that time onwards is just the same alpha that we had initially. And as a consequence, we get this identity for the quantity alpha. That means that we can estimate this infinite horizon discounted reward, which, by the way, is not something that can be easily simulated without a trick of some kind, because of course, this infinite sum involves the infinite horizon behavior of the Markov chain. In principle, to actually generate this random variable would take infinite time. I'd have to generate the Markov chain's trajectory all the way out to infinity. So we've replaced this non-simulatable quantity by something that can be simulated, involving finite horizon quantities. And in particular, if we take this identity, we can write alpha as the expected value of the discounted sum of the rewards up to the return time to state X divided by 1 minus the expected value of the discounted hitting time tau of X. This is something that in turn can be written as a smooth function G of this expected value and this expected value. In particular, the G function in this case is just Z1 divided by 1 minus Z2. It's just a simple illustration of that smooth function model. In some settings, we're interested in doing steady state simulations. We're interested in equilibrium quantities. So in particular, imagine that pi is the equilibrium distribution of the steady state distribution of the Markov chain. And we want to integrate some reward function against the equilibrium distribution. We want to compute the expected reward associated with steady state. Let's call x infinity a random variable having the equilibrium or steady state distribution of the Markov chain. The natural way to do that is to run the Markov chain for a long number of time steps n, look at the average reward over that long time horizon, the so-called time average. That time average in great generality will converge with probability 1 to alpha. That's a consequence of the law of large numbers for Markov chains. There's also going to be a central limit theorem in great generality for that time average. But the challenge now comes in trying to estimate this variance constant sigma. And the difficulty comes about as a consequence of the fact that these R of xi's are correlated. And as a consequence, the variance sigma squared is something that involves this nasty infinite sum involving covariances of the rewards taken j time steps apart. We're looking for the jth term involves covariance between r of x0 and r of xj. We're looking at rewards taken j time steps apart, and we have to sum up all of those covariances. So that time average variance constant sigma squared is a nasty object to try to estimate. And so there are lots of different simulation settings in which variances are hard to estimate. Smooth functions of expectation, we talked about that. Steady state simulation. Stochastic gradient descent turns out to be another one. Quantiles, yet another. Many different simulation settings in which it's hard to estimate variances, therefore hard to construct confidence intervals. So now let me give you.
Can I interrupt you just for a sec? Yeah. So you were talking about smooth functions and doing inference. We had a talk earlier this week where we were told about non-regular inference and what happens when G is non-smooth. You get all sorts of weird behaviors. The limiting distribution can abruptly change under very minor perturbation in the system. So I was wondering if the stochastic simulation community has thought about problems where G is non-smooth. Maybe G is like this famous problem apparently called max of means, where G is just the component-wise max. And there's some work in statistics on that. I was wondering if you had any thoughts on that. G is non-smooth.
There's lots of settings where you have that type of issue coming up. And there are special purpose methods that people have created for specific types of problems. I'm going to give you a general tool in a couple of slides that addresses that issue to some degree.
Oh, great. Thanks.
So let me first of all talk about a setting that deals successfully with the smooth function setting and with steady state simulations.
There's one clarification question before we move on to something else. On slide 17, the last line, some confusion as to why z bar n became z.
Z bar n becomes so is it at this point why I have an expected value of z sitting in here, or what?
No, I think the last line. We have z bar minus expectation of z, where you were pointing at, and the very last line in expression for sigma squared.
Yes.
You have z no z bar n.
Right. So that's because it is the case that the quantity alpha n has a variance that looks like sigma squared divided by n. But in the way I've written this limit theorem, the 1 over n is already captured in the scaling square root of n.
Mm-hmm.
So this is basically the variance per observation at some level.
Right.
So there should be no n in this quantity.
Yeah. Basically taking a square of the previous expression, taking expectation, and identical distributions expense it all, right? And the scaling.
Yeah, exactly right. Yeah, thank you. Okay, so let me come back to this replication method. So this is a method that can be used in lots of settings in which you know that there's a limit theorem in which the limit random variable is normally distributed with mean 0 and potentially some complicated covariance structure or variance structure. So again, the key thing is the right-hand side is normal with mean 0. So if you have that, then here's one thing you can do. You can just take your algorithm and run the whole algorithm, let's say m IID times. So these are the replications. And then each of these replicated estimators satisfies this limit theorem, which means, of course, that for large values n, the estimator alpha ni coming from replicating the algorithm on the ith iteration looks approximately like a independent normal with a mean equal to the parameter that we're trying to compute and with a variance that is the variance associated with this particular limit theorem, which again, if you square both sides and you assume that the variance of the left-hand side converges the variance of the right-hand side, that would be telling us that the variance of alpha n looks approximately like sigma squared n divided by a squared n for large values of n. So that means that even if you only replicate this algorithm twice, you'll have two of these different alpha n i's. These alpha n i's will look approximately normal with mean equal to the quantity that we're trying to estimate and with unknown variance. And of course, statisticians have a nice solution, have a nice answer to how you construct confidence intervals when you have unknown mean and unknown variance. That takes you into the world of student T confidence intervals. And so now all you need to do in this context is just apply that methodology. We have unknown mean alpha, unknown variance sigma squared over a squared n. Just apply that standard statistics methodology in this context. And there you have now a confidence interval to deal with this setting. You never, this procedure avoids having to explicitly try to estimate the variance parameter sigma squared. Right, now there's another approach which can be used in settings where the right-hand side is not normal with mean 0 and some potentially complicated variance. And this is to use the method of subsampling, which was developed actually fairly recently in the last 20 years or so by Joe Romano and company. So here's the way subsampling works. So suppose that you now have a Monte Carlo algorithm in which we know that this type of limit theorem holds. So there's some value of a, and a typical Monte Carlo algorithm, a would be equal to a half, so you'd have square root scaling, but it doesn't have to be square root scaling. And n to the a times alpha n minus alpha converges to w. So if a is positive, this is saying that the error is shrinking at rate n to the minus a. And that w can be a very complicated random variable. We don't need to even know exactly what its distribution is. It can include nuisance parameters, all kinds of nasty things. And now the point is that if we choose a subsample m that's significantly smaller than n, then we know that if m is large but not as large as n, then n to the a times alpha n minus alpha should be approximately distributed as the random variable w. That's according to this limit theorem up here. We don't know alpha in general, but if m is much smaller than n, then alpha n has a precision that is so much higher than the precision of alpha n itself that effectively we can substitute alpha n for alpha and get something that has approximately the same distribution. And now the thing that's nice about this is something that is computable and constructible. So in particular, if we now just construct multiple subsamples of size m from our n sample, and we just collect an empirical distribution of these quantities, this empirical distribution should be roughly the empirical distribution of w. From this empirical distribution, we can now select a w1 and w2 such that the probability of coverage within that interval w1 to w2 will be approximately, let's say 90%. And now we just plug in that w1 and w2 into the original sample size n, and we get a legitimate confidence bound for the for this Monte Carlo algorithm. So there's a Monte Carlo procedure for getting confidence intervals in settings where estimating variance is hard, and maybe even the entire limit distribution W is close to intractable. As you may have seen earlier today, or maybe earlier in the week, there are a number of settings in the world of stochastic optimization where the limit random variables W can be non-Gaussian and be quite complicated. This is potentially something that can be used in those settings. Then the last thing that I want to just say before we finish this first lecture is that many of us these days are thinking about trying to do computations in massively parallel computing environments. And one thing to be aware of is that there can be sometimes significant challenges that arise in the Monte-Carlo context due to completion time issues. So let me just say a little bit about that. So suppose that I want to estimate the mean of a random variable W, and let's suppose that the random variable W is simulatable, so I can run IID replications on different parallel processes. So imagine we have a large number P of parallel processors available. I'm going to run for C units of computer time on all P processes. Now, one thing that you might think about doing is I will average the number of completed replications on each of the P processes and form a sample average W bar IFC. Here, the random variable NIFC is the random number of replications of W that is able to successfully complete on the ith processor within computer time C. And then, of course, we can just average over the P processes. Then we get the expected value of W bar of C plus a normal error that decreases at rate 1 over square root of P times C. 1 over square root of P times C, because of course the total amount of sampling time available is why you have P processors, you have computer time C available on each of the P processors, so total amount of computer time utilized over all P processors is P times C, and we have a square root convergence rate. So you should have this thing scaling down at rate 1 over square root of PC. But now we have to look at this quantity here, and we can see that if the number of processors P is large, it could be that this bias, this thing, expected value W bar of C is not exactly equal to the quantity that we're trying to compute. So when P is large, maybe that what you're computing, what you're by averaging all these different quantities, is something that is dominated by the bias, dominated by how far away this expected value is from the true thing that you're trying to compute. And this bias issue that arises because of the fact that W bar of C is a biased estimator can have can complicate the analysis in these types of massively parallel computing environments. There are different types of fixes that are available, and that's something that I looked at in a bunch of papers with Phil Heidelberger from IBM back in the 1990s. That might be relevant in the current context and current times as well. All right, so that's the end of my first lecture. In the second lecture, I'll talk about variance reduction and gradient estimation. So thank you. So we'll be back, I guess, at 2 o'clock.
Thanks, Peter. There is one follow-up question that came, which was about constructing the confidence intervals for the subsampling section.
Yeah.
Could you give a bit more detail as to how we would actually learn or use the estimates to construct the confidence interval? Are you just taking the error quantiles, or?
So, right, so the key issue here is constructing these subsample quantities. Now, in some settings, it won't be hard to do that. So for example, in the context of the smooth function model, if I wanted to use subsampling in that context, I don't think that would be the right thing to do in that setting. I think what you would do in the smooth function setting is you would use the replication method, potentially, or something like that. But if you wanted to apply subsampling, you do have to construct the estimator's alpha M from the, corresponding to a subsample of size M. Now, it could be, that you just run, just take whatever algorithm that you had initially, and you reinitialize that algorithm and, run it with independent random numbers. That gives you an alpha M, and you do that a bunch of times. And that gives you the R different subsample quantities. You might be thinking to yourself, well, that seems extremely inefficient, and it is inefficient. That's why you wouldn't use subsampling unless this is basically a last resort to the situation. But in some contexts, the computational complexity required to compute alpha M is a function of the number of samples M taken. scales non-linearly in the sample size. So, might be, for example, in an optimization context, it could be for various reasons that the complexity of computing alpha m doesn't grow linearly in m. And then computing alpha m for relatively small values of m as compared to n could be a fairly small computational overhead relative to computing alpha n itself. So having to do these sort of independently generate a whole bunch of alpha m's corresponding to much smaller sample sizes than the n that we use for the sort of grand estimate itself could be something that would be practically viable.
And just to clarify, in case people are getting confused, this W is just a placeholder here. It's not the same W that we started the talk with, whose expectation is alpha, right? Like there's no reason why this limit will be this.
Yeah, thank you very much. Yes. Sorry for confusing you. If I confused any of you by using the same, yes, it's a completely distinct random quantity.
Thank you.
So I mean, one setting where I've seen this come up myself is in settings. For example, you do random sampling within the, let's say, a hypercube to try to identify the minimum of a function over the hypercube, and where the function evaluations involve having to run simulations at the different points in the hypercube. In that context, when you develop a limit theorem for that type of estimator, the right-hand side actually turns out to be quite a messy object, not something that you'd want to work with, and it would be an object that has lots of messy nuisance parameters in it as well. So it's not like the normal distribution where the nuisance parameters are a scale and location parameter. You can easily deal with them as a consequence of that scaling location characteristic. The nuisance parameters that arise in that, in the limit theorem for that, the type of algorithm I just described, is enter in a very, very messy way.
And then you said earlier that getting information a priori about, let's say, the bounds of the random variable, this is hard in typical situations. It's this type of information is either not available, or if you give some very large bounds, then the confidence intervals you'll get will be uninformative. Did I interpret you correctly?
Yes, I think that's correct. And for example, in the Markov chain context, if you want to get an a priori bound, for example, on this time average variance constant on this sigma squared, this would be very, very, you could do it. There are mathematical methods available to bound the sigma squared in the Markov chain context. But I think it's fair to say that the bounds that you would get in a typical application would be probably close to unusable.
Oh, sorry, and one more clarifying question before I guess we take a break. Would you mind going to slide 18, please? Questions about how you got alpha on the right-hand side in the final formula.
Right. So this maybe becomes clearer if you just write this infinite sum as a sum of the discounted rewards up to the return time to the state x. So that would be a sum of like this. So that's, and then I have the sum from tau of x to infinity. And I'm going to write this by factoring out the common discount factor. So this thing would have an eta minus alpha j up here. But all of the j's that are sitting up here have j greater than or equal to tau of x. So I can write this as also as k plus tau of x, where now k is ranging from k equals 0 to infinity. I'm just doing a rewriting this piece, and now I'd have rewards that involve the post tau of x Markov chain. So in other words, involve the path of Markov chain beyond time tau of x. And then I'm just using the strong Markov property to say that eta minus alpha tau of x is independent of the random variables in this sum. So I'm writing this as eta minus tau of x, and summation k equals 0 to infinity of eta minus alpha I times r of x, tau of x plus I. This quantity here has exactly the same distribution as this random variable, conditional on having come back to the initial state a second time. And strong Markov property says that these two random variables are independent. So the expected value of the product is the product of expected values, and I get this piece.
Thank you. That makes a lot of sense. Would it be? Yeah. Sorry, Java.
Yeah. Sorry. Just for the same slide. So alpha appears both in the exponent and both as the definition of this exponent.
Yeah, it's a bad. Let me put C here.
I think that was maybe what led to the question, I think.
Well, that's a very good. It's an unfortunate use of notation on my part.
Yeah, different communities tend to use different symbols.
Well, in any community, you don't want to have alpha meaning two different things on the same slide. So that was just a mistake on my part.
Would it be possible to get these slides and also the slides from part 2 so you can follow along?
Yep, absolutely.
Perfect. That would be really helpful. I don't see any more questions. Last chance for anyone. Otherwise, thank you, Peter. I think we resume at 2 o'clock.
Great, thank you.